In this video, we're going to cover the next two possible terms, our zero at the origin and our pole at the origin. So first, our zero at the origin, we can see is represented just as our j omega to the power of 1. And so we have our sort of basis for our Bode plot. We want to know our magnitude information so we can plot the gain in decibels. And we want to know our frequency information, our phase information, phi, and both of these we're plotting against frequency. So let's look first at our magnitude. Well, actually, let me take a step back and let's talk about this j omega. So if we look at the j omega in our complex plane, so if we have our imaginary axis and our real axis, we see that j omega has no real part. It is purely imaginary. So what that looks like if we were to put a point on this complex plane, it would be right here. And so that would be at a value of omega. So we can see that the magnitude, the distance from the origin, is just going to be omega. And we'll come back and we'll talk about the phase here in a second. So for our magnitude, the distance again is going to be omega. If we want to put it in decibels, we're going to then have 20 times log of omega. Okay, so that's going to be our our magnitude information. So let's think about a couple values of omega to help us plot this. So we know that if omega equals 1, we have log of 1, which is 0. So let's just say if our frequency is 1, we're going to be at this point here. Now, what if, you'll notice I have a couple other points already here, so what if our frequency is 10? So if we have omega equals 10, log of 10 is 1, so we're going to be at 20. So let's go ahead and label this as 20, and we're going to put a point right here. So if our frequency is 10, we have a gain in decibels of 20. If we go the other direction and we make our omega 0.1, we see that that is going to make our log of 0.1 negative 1. So negative 1 times 20, of course, is going to give us negative 20. So negative 20 here. And so we're going to have our third point at that intersection there. So we have something that looks like that. So now we can connect these lines to sort of get an idea of what this looks like. And of course, this is going to extend on in either direction. But the important thing to note here is that we have a slope, and our slope is going to equal to 20 decibels per decade. So 20 dB per decade. And so per decade is, of course, just if, for instance, if we're going from 1 to 10, that's a 1 decade increase. And so we're saying if we make that 1 decade increase in this case, we are increasing by 20 decibels, as we see from going from 0 to 20. Okay, so that is for our magnitude. So now let's look at our phase. So if we first come to our complex plane here, we see that our angle is going to be 90 degrees from our real axis. So our phase is just going to be 90 degrees. And so of course that doesn't have any frequency dependence. So we can come up here and we can say we're at some point here, which is just equal to 90 degrees. So that's for our zero at the origin. So now let's look at our pole at the origin, which is going to be very similar. So now we have j omega to the minus 1. So again, let's start by considering what this looks like in our complex plane. So let's draw our complex plane here. So we have our imaginary axis and our real axis. And we have j omega to the minus 1, which is, of course, 1 over j omega. Now, we can show that 1 over j equals negative j. So this is actually negative j divided by omega. Or to make it really clear, we can say this is negative 1 over omega times j. So again, this is purely imaginary. We have no real part. And we see in this case, we're going down by a value or a distance of negative 1 over omega from our origin. So if we put this point here, we're going to be at some place here where this is negative 1 over omega. So that's the distance from our origin to that point. Okay, so let's talk about that magnitude then. Okay, so our magnitude is going to be negative, sorry, not negative, let's take this one step at a time here. So we say 20 log of the absolute value of this magnitude here, which we can see is going to be 1 over omega. Well, I can write that as 20 log of omega to the minus 1. And then I can use my log properties to bring that negative 1 down and write what I wrote at first there on accident and say that this is negative 20 log of omega. So we see this is the same form as what we had for the 0 at the origin. The only difference is we have this negative sign out front. So let's see what that means. So again, if we consider omega equals 1, we're going to have log of 1 is 0, so we're going to be at 0. So we still have this same point here. So now let me go ahead and label this as 20 and minus 20. And so what we can see is if we plug in 10 for omega, log of 10 is 1. So now for 10, we're going to be at negative 20. So let me actually draw this first. And so we're going to have a point there. And then if we went the other direction and we plugged in 0.1, log of 0.1 is negative 1. Negative 1 times negative 20 is going to give us a positive 20. So we're going to have another point on this line here. So we can connect those three, and again, that's going to keep going in either direction as our frequency increases or decreases. And so we notice it's the same sort of form, but now our slope is just the opposite. So our slope is now equal to negative 20 dB per decade. So as we increase a decade, we're decreasing our gain by 20 decibels. So now let's come down here and consider our phase information. So if we come back to our complex plane and we're looking at this point here, we notice to get there from the real axis, we have an angle of negative 90 degrees. So for our phase, just like with our 0 at the origin, we're going to see we have no frequency dependence. And we just see that our phase is negative 90 degrees. So coming up here to our phase plot, we would just have negative 90 degrees and just constant without frequency dependence. And so let me make sure I put, so 90 degrees up there, negative 90 degrees down here. So we can generalize this and say, well, what if we had, instead of j omega to the 1, let's say we have j omega to the n. So generalize and consider j omega to the power of n, where n is just an integer value. So this sort of already encompasses the two cases we've looked at, right? Because 1 and negative 1 are both integers. And so what happens is for our magnitude plot, we're going to have a slope that's equal to 20 times capital N dB per decade. And for our phase plot, we're going to have a frequency independent phase with a phase angle that's equal to 90 times n degrees. So sort of as a simple check, we could plug in 1 and negative 1, and we see that both of those cases check out with what we've just covered for our simple pole and simple 0, our pole and our 0 at the origin. So for instance, if we had j omega to the power of 2, we see that would give us a 40 decibel per decade slope, and we would have a 180 degree phase angle. So that's how we use this general information here.